specifically today we'll get started with electrical circuits. Okay. Notice, as far as the GATE biomedical paper is concerned, what I discussed kind of specific to, the marks distribution is specific to biomedical paper. If you look at GATE BM paper, you have general aptitude, this is general aptitude and math together. This makes 15 plus roughly 12, that is 25, 27 marks. Okay? So rest of the 73 marks, we have core biomedical subjects like biomechanics, biomaterials, medical imaging, bioinstrumentation, anatomy and physiology, core BM. Okay, they're subjects. And then we also have core as in again, not G and math, we have non-BM subjects, electrical circuits, signals and systems, measurements, controls, and analog and digital electronics. Typically, the marks distribution here is core BM questions have a higher weightage. Okay, so out of the roughly, let's say 75 marks is left, 40 to 45 over here, 40 to even I would say sometimes 40 plus marks is 45, approximately 45 marks in this side, and here you have approximately 30 marks. These two are approximately all three add up to 100. Okay, so you can get a single digit all India rank. Notice around 50, 60 and all that, you're a single digit topper, right? Even 45 you're a topper. If you focus on this, do well, this is you can excel in the GATE biomedical paper, get even a single digit rank. By that, typically get a seat of your choice. But there are also some easy questions here that biomedical students can get an advantage or can get a lead, right? Can get an edge if they manage to get a couple of marks here. Anywhere from 10 to 15 marks, if they manage to grab here, that's a very, very big advantage. And typically there are 10 to 15 marks worth of easy questions in this side. That is one reason to learn this. And another reason to learn this is, hey, you are not a biomedical student. You are from a different branch, instrumentation or electronics student. Okay. Again, notice, if you are very, very strong in this non-BM course, non-BM subjects, try to score as much as possible. Then you have to be reasonably good at GA and math. Learn basics of biomedical as much as you can, at least bioinstrumentation, medical imaging and all that. Then again, you can put up a very good fight. If you also manage to learn advanced things over here, you are a candidate for even all India rank less than 5, something like that. So this is the reason to look at this non-BM subjects, electrical circuits being one of them. Having said that, at this stage, we are like October, right? So we still have about 3 months till the GATE examination. Most of us will start putting more emphasis on practice, revision, mock tests at this stage, certainly by December, right? You may not have all the time to learn everything in electrical circuits, okay? But that is where, notice, if you look at the GATE syllabus, this is, let's say, GATE BM syllabus, there is a small subset here, approximately 20%, where 20% of concepts, where 80% of questions show a small subset of the concepts in the syllabus is where typically most of the questions are concentrated. Typically, okay, this applies to GA, math, core biomedical, non-biomedical, most of it. And every year questions don't repeat, but these concepts keep repeating. So if you learn the PYQs in and out, okay, you need to know them in and out, so that if you understand the underlying concepts, related concepts, you are likely to do very well in the upcoming GATE exam. Okay, most of these concepts will repeat, and if you are kind of thorough with them, you are likely to perform well. Again, if you at least the easy moderate questions, it's very, very easy to do. That is the reason we are going to start looking at the PYQs from GATE biomedical papers. Okay, so far notice we have 4 or 5 years of PYQs, right? This is 2020, 21, 22, 23. 4-year question papers we'll look at it. We'll use a 4th year paper, 5th year paper, 2024 as a mock test. Okay, we'll see where we stand. We'll use it for that. And again, my suggestion is, typically, if you look at, even the PYQs, there are easy moderate and hard questions. It makes good sense to actually put your focus here. It's most efficient in that sense. Okay. Else again, you seem to be forgetting what you learned in bioinstrumentation 2 weeks back, right? Cramming more and more things is not productive. Typically, it's counterproductive. Okay. So some bare minimum things that we want to learn in circuits, that is what we are going to learn. And the reason being, of course, the concepts don't repeat. I mean, concepts typically repeat. Okay? But if you look at the questions, PYQs, they don't repeat. But even as we look at the list of PYQs, I have kind of clustered them into different sets. We kind of recognize, the concepts keep repeating again and again. We'll make sure that all the easy, moderate concepts, all the questions will learn very, very. Okay. That is the objective. That is what we'll be doing this month. We'll go one subject at a time. We'll go circuits, then we'll go measurements, signals and systems, controls, then electronics. Okay. Now let's get started with resistances. So circuits that only has resistances, I want to know where the class stands. Okay. Let's do a quick poll. So check all that up, right? So let's make it a multiple choice. One is to do equivalent resistances, series parallel resistance. Right? Familiar with equivalent resistance. Say familiar with them. Let's simplify it. Let's be more specific. Check all that. You are familiar or comfortable with it. Okay? I'm going to say familiar. One is series parallel resistances. This is specifically concerning resistance, circuits with resistances. And then can you do Norton and Blend conversion with independent sources, no dependent sources? If you know, you kind of follow and simple Norton Thevenin conversions. Next would be, can you do, let's say, what do we have here? Basic power, related variables, basic variables like power, energy calculations. Can you calculate what is a power dissipator? What is the energy, total energy dissipator? What is the rate at which power is dissipated? Can you make some basic calculations? And every year there is also a question from a specific type of circuits that only has resistance. Okay, and this is known as a Wheatstone bridge. This shows up in high school physics. Are you familiar with that? Kind of aware of what is this bridge balance? Okay, let's do this poll. I just want to know where you stand. Based on that, I will kind of tune this. So I'm starting to get answers. So most of you are saying you could do series parallel resistances. Fair. If you have to add one trick, in your hat, that would be delta star conversion. Okay. Why delta? No, delta star conversion would be one thing that I answer. Fine. So most of series parallel, you could do other things only like half the class kind of is aware of it, right? Fine. I presume that is also the case with voltage division, current division. But that's fine. Okay. Yeah, there is a couple of voltage now. Fine. So equivalent resistances, all of you in kind of know this is, you have series, parallel. Some moderate level questions will also ask you delta star or delta Y conversion. This is where you have resistances like this. You have three terminals. 1, 2, 3. You can convert that into an equivalent 3 terminal this way. Or if we keep the terminals as such, or 3 terminals, you could convert this into 3 resistances this way where there is a load over. Okay. You can make this conversion. This is, some moderate questions kind of ask this. If you know this, that is very, very okay. So I'll explain, at least I'll introduce you what Norton Thevenin is. Basic power calculation. You all know this, right? So power dissipated is I square on. Right. Notice power is in a DC circuit is fairly simple. This is just I square. And then again, Wheatstone bridge, I'll kind of explain what this is. You have to know few other things. That is basic voltage law. Kirchhoff's voltage law. Kirchhoff's current law. Okay. This is KVL as this, right? In a closed circuit, right? In a closed loop. Increases and decreases in voltage add up to 0, right? KCL, if you take if you take a part of a circuit, the current entering and exiting, net current is 0, right? What enters this boundary should be what exits. Let's say current enters at 2 places. What exits should be equal to what enters. Provided, nothing is kind of stored anything. As far as this boundary is concerned, what enters typically equals what exits. This is KCL. We'll also look at examples on the Kirchhoff's current law and then Kirchhoff's voltage law. And the rises in potential. There are a couple of places where voltage increases, and then there are a couple of places where voltage drops. They'll be the drops and rises kind of equal. This is one thing you want to know. In addition to that, you also want to know division laws. You have basically two divisions. Okay, one is a voltage division, and then you also have current. So typically, notice. Let me just strike this one now for a time. Typically, there is a question from this. The list that I have shown here. It's fairly very simple. On top of that, almost every year, there is a question from Wheatstone. If you are lucky, there are two questions from Wheatstone. One from DC, one from AC. Okay, so we'll cover most of this. Let's look at this question. Okay, Gate BM 2020, the nearest value of power dissipated and 3 ohm resistance in the circuit. Okay, we'll go ahead and answer this. Before you kind of answer that, can you all tell me your approach to solve this? You could answer that in the chat. What is your approach to solve this question? This question again can be solved in many ways. Find the current and I square R. So you want, okay, so now, okay, the suggestion is find I. How do you find I? Right, you find I, then the I square R is the power dissipated. Fair. How do you find that I? Current divider law. You have to be little more, specific, okay? Because current division directly is not applicable, but so we have to do a couple of changes here. See, those who are thinking current division and all that, there is one more voltage source here. There is a current source here. There is a voltage source here. It's not like this 2 amp is going to split in this way, right? You have to account for this voltage. You have to take care of that. Yeah, now I'm starting to get, many of you are starting to improve your answers. Convert voltage source. See, there are two sources. And can you deal with them? Can you make it like similar sources? Source transformation and all that. If you do source transformation, perhaps things get easier. Okay. And then another thing is, hey, can you simplify the circuit with minimum resistance as possible? Yeah, again, you are kind of doing a source transformation. Girish is saying, hey, can you do nodal analysis? Okay. Notice, this is a reasonably, this is a moderate level question. Not like they are not spoon feeding you with the answer. Okay. This is a moderate level question. This is fairly easy. Now, we can do this in a couple of means. One is apply KVL, KCL. No, solve KVL and KCL. You can solve that. Okay. Another thing is, hey, there are too many sources. Can you do source transformation and simplify? Okay. Now, you could, can we do, there are a couple of other ways, but, I think these two typically kind of will give you the answer very, very fast. Can you do superposition? Yeah, but, it's much easier to do some of this. So, two sources are kind of hinting at me thus. There is something else in the circuit that is hinting at me to use this. Presence of two different independent sources, a current and a voltage, is suggesting me, hey, try source transformation and simplify. There is another detail in the circuit that is suggesting me you could also solve this quickly using KVL KCL. Okay. So first, let's learn this. What is a source transformation? We'll solve that. And then perhaps that involves a couple of, probably involves a couple of details. Let's do this one at a time. So we have source transformation. Typically any linear circuit, okay, just voltage resistance circuits. Let's say even independent voltage current sources. Let's not even bother about dependent voltage current sources. Okay. There are some complicated circuits. Okay. Notice. So again, if I have to give you an analogy, notice, all of you know if there are two resistances in parallel, equivalently simplify this to one equivalent resistance. Now, what the source transformation is saying that you have a circuit with many voltage sources, many resistances. Okay, let's say there is a current source. Typically, in the source, there is, in applications, there is a load kind of thing across which you put your primary application. Typically, it's a resistance. Okay. So, load is connected to two terminals. This is referred to as the load, typically a resistance. Okay, or yeah. What this transformation law says is, you can take this circuit, okay, any linear circuit, you can take this chunk and simplify that. Okay, so across these two terminals, the rest of the circuit. Now, notice this one resistance or equivalent. This is equivalent to these two, right? Essentially, wherever this is, you can replace that with the single resistance. Like that, wherever the circuit is, you can equivalently replace that with, okay, interestingly, a single voltage source and a single resistance. If you had to complete the circuit, we can connect the load, and this is what we have. So the circuit that I have circled is equivalent to this. This transformation is referred to as Thevenin, and this voltage, equivalent voltage for this entire circuit is VTH, and this one resistance for this entire circuit is referred to as RTH. Okay, so this is VTH and this is R. This is known as the Thevenin equivalent. We also have a Norton equivalent, where again this entire circuit could be equivalently written as this. You have a current source, okay, in parallel with a resistor. You have this current source value is this is INO, this is RN. This is referred to as a Norton A. So circuit, this big circuit, any circuit can be written as either in the Thevenin form or in the Norton form. And they are all equal, so you can also go back and forth between this side and this side. So the question is, now we have two questions. How do you go from here to here, right? How do you go from here to here? Then how do you go back and forth from here? There is a question 1, then there is a question, how do you do this conversion? Question 2 is fairly easy. Question 2, right? So your notice. So given Thevenin Norton is fairly simple. Can anyone say what this I Norton is? Just from the V Thevenin, take the Thevenin voltage divided by Thevenin resistance. And one thing that really makes your life easy is the resistance doesn't change. So this happens to be R Thevenin, and this happens to be R Norton. So given R Thevenin, you can directly write R Norton. Given R Norton, you can directly write R Thevenin. So I Norton is this much. Say Norton circuit is given. How do you find the Thevenin voltage? V Thevenin is just IR. Take the Norton current. Norton, there is, R Norton is R Thevenin. Just take this resistance, multiply that. So this is how you deal with 2. Let's kind of color code this. This is how you deal with, you can go back and forth. Then there is a question, how do you do 1? We'll come back and answer that. Okay. But right now, let's go back to that question. Hey, there are 2 different sources. So use source transformation and simplify. If you know the current, it kind of simplifies, right? We could do it either way. But I am going to do, let's say, I'm going to convert this to Norton. So notice, these 2 can be easily clubbed together. No issue. So I'm going to draw a couple of conversions. Your task is to tell me which conversion is correct, where the values are. We have a 2 here, 2 amps. We have a 3 ohm here. Okay. We have a 4 here. We have a 4 here. This current will be 0.5. Option 1. Option 2. So what I am doing is trying to replace this chunk, if you're wondering. So I am trying to convert, it's a Thevenin circuit, that bit across these 2 terminals, right? I'm trying to replace that with a Norton equivalent. So this is one option. Let's continue in this. Yeah, this is one option where we have values, let's say 4.5. Let's make that 2. Let's make this 2. This is 0.5 and this ohm is 3. Okay. Third option is, let's say, we have a 3, we have a 2.5, and then we have a 2. We have a 3, we have a 2.5, we have 2. So right now, task is pick equivalent circuit. Pick equivalent circuit. You have 3 options. It's an MSQ. Option 1 is this. Option 1. Option 2. Option. So all are equivalent. Someone says option 1. General says 1, 2, 3. Again 1, 2, 3. So I have to give credit to everyone. Option 1 is correct. If you take that yellow chunk, if you replace that, option 1 is correct. In fact, let me color code this where you have, I'm going to write on the same impulse. Okay, so this is 0.5 and 4. In fact, again, if you have to write this in, from the Thevenin Norton resistance is the same 4. Norton current is 2/4, that is 0.5. Okay. This is where I also notice these are connected, there isn't any resistances. These are all the same potential. These are all of the same potential. Same potential. Essentially, they all behave as one single point in the node. Let me repeat that. Okay, notice if I look at this point in the circuit, this point in the circuit, the potential is essentially the same. They are connected by wires with no resistance, negligible resistance. Same goes with all these are at the same point. For the same reason, all this behave as a single point. For that reason, if you change the order here, it doesn't matter. All the points here are essentially there is one point in the top, there is one point in the bottom. Okay, if you were to write this in a different order, it's essentially the same set. Thus, this is essentially the same set. So we have a 4 here, we have a 0.5. I can change the order. If you want me to slightly, notice, I clubbed these two resistances into this bit that stays here. You call this, whether you call this yellow glow, doesn't matter. But that chunk went here. Okay. So 1, 2. Do you agree with this? 1 and 2 are essentially the same. We'll go to 2 in a moment, but 1 and 2 are essentially this. Anyone has questions? Because essentially there is one point in the top, one point in the bottom. If you change the order, it doesn't matter. Now what I have done is same thing. I have clubbed this to this 2. Then I have clubbed, here's the blue already. Then, I clubbed this to this. These two 4 and 4 in parallel make 2. Current source of 2, current source of 0.5. Notice net outflow from the 2 to this node is 2.5. This to this rose node. Net outflow here is 2.5. Net inflow here at the bottom is 2.5. They are in parallel. The two currents get added up. I have done that conversion over there. For that reason, 3 is also the same. So pick equivalent circuits 1, 2, and 3. All 3. And directly writing down 3 may not work, but typically you will have to either write down. Typically you write down 1, and then from 1 you write 3. Just to highlight, this order and all that doesn't matter. I introduced 2, okay, and to also explain this, how it looks and how it functions. Sometimes is confusing in circuits. You need to get used to it. The looks as such are deceiving. You have to go by the functionality, equipotential points and all that. So typically you do step 1. Then 1 you simplify that to step 3, and at step 3 you have the answer. Okay, so 2.5. How much of this will get split in 2? How much of this will go into this 2 ohm resistor? Does anyone know that? So I have 2 methods for this. 2 easy methods. Let's look at this method 1 or method 2. Okay, given circuit becomes circuit 1, that becomes circuit 3. At 3 we can answer. Given circuit becomes 1, that becomes 3. At 3 we can answer. Can anyone say how to answer this at step 3? If this is not somewhat visible, let me also find out that. Let me, if you're later on reading this, which happens. Current division rule. Alright? So notice. So whether you write it this way or you, again, it's one node at the top, right? Whether you write it this way or this way doesn't matter. You can change the order of the resistance, because at the top you have one node essentially. At the bottom you have one node. You have a 2 and 3. Now the question is, how does this current split between 2 and 3? You could answer it at this stage. Okay. So ideally you are coming from 1 to 3. Okay, at 3 you can answer. So you have current division and voltage division rules. Voltage division and current division. This is a circuit like this. You have 2 resistances in series. Let's say this is grounded. You are using that as 0 potential. Let's say you are measuring potential with respect to that. If I have a source voltage V here, right? Essentially I have, let's say, at the top, the voltage that I have here is V, and these 2 resistances are R1, R2. Question is, typically we measure the voltage somewhere here. What is this voltage? This voltage. Sometimes typically we refer to this as the input voltage. Say as in a potentiometer, we refer to this as the out. It says output voltage. It's a fraction of input voltage. It's a fraction. It cannot be greater than input voltage. Somewhere between 0 to 1 times input voltage. That fraction happens to be R2. The bigger this resistance, higher this voltage drop. So you have R2 by R1. Notice this is a fraction. This is essentially a fraction. Output is a fraction of, this is known as voltage division. And when can you say that? In this, as far as this, this edge is concerned, this part is concerned, there is no current going out, no current exiting, somewhere in the middle. As far as that is the case, you can apply this. No current exits in the middle. But the circuit that we had is slightly different. No, we had a circuit like this. You have a current source. That current gets divided between two resistors. There is a net current entering and exiting this. Notice current I enters this, it should exit this. And again, we have resistances R1, R2. Question is, what is I1? Current in this resistance R1, current in this resistance R. Again, I1 is a fraction of the input current, total current entering. It gets split between these two. So it's a fraction of that. But how does it get split? Smaller this resistance, more current flows through it. Okay. So it's a fraction. Again, the term that you're going to have here is R1 plus R2 in the denominator. But bigger the resistance, lesser the current. Bigger R1, smaller is I1. Okay, more resistance to current flow. So what flows through I1, what flows through R1 depends on proportional to R. You could also, of course, compare this I2. Notice, again, this is a fraction. Notice, this is the fraction of what is in here. I2 happens to be R1 by R1 plus R2 into what is entering. No confusions. With fraction. That is your current division. So in our given circuit, 2.5 amps is entering. How does it get split? Okay, easy. Let's go back. That question, essentially, notice there is a 2.5. There is a resistance of 213. How much goes into 3? At this stage, I can erase 4. Okay, I don't have to bother 4. 2.5. How does it get split divided between 2 and 3? That's fairly easy. So your current through R3 equals the total current entering, that is 2.5. Fraction of that depends on, it's proportional to the other resistance too. Denominator of bit 2. So this is 2 by 5, this is 5 by 2. I suppose this equals 1. And your answer is in power dissipated. Power equals I square. R3 is a subscript in R3. That is 3 watt. This is in amps. Everything is in ohm SI. So ampere square into ohm, that should give you watt. V equals, RA. Voltage equals, right? Volt equals ampere into ohm. Ohm ampere. That into ampere gives you power. So your answer here is 3. And what I just discussed, this method. There are many other methods, but you can, if you're comfortable with this, you can fairly, get this. Yeah, do this transformation. Then, problem is 2 sources, transformation. Hey, this is actually simple. Couple of resistors in parallel. How does the current get split, right? Total current is 2.5 at that stage. Get split. So this is method 2. Any questions? Method 1. KVL and KCL. KVL and KCL. But how do they apply Kirchhoff voltage law, current law? There is actually something suggesting me, hey, actually even method work will give you an answer very, very quickly. Can someone spot it? And I have given you some clues. I have already given you some clues. Can someone spot? It's actually fairly easy to find this. You can get the answer, no transformations, but you can write one equation and get the answer. And there is a very specific reason for that. So sometimes gate, I say, hey, this is a 2 scenario gate question, right? Scenario 1 to 2, scenario 2, typically you divide or something like that. Some common terms get cancelled. Simple algebra gets cancelled, right? Things are displayed in proper. Like that, this is a specific type of circuits problem. Very common type of circuits problem. Just in case on the day of the exam, which conversion to do, you are not clear. Okay? Somehow, that day you get confused with how do I go from, some of these things. Should I do theorem? Sometimes the confusion happens. You ask, is it a single variable problem? It is, right? A single variable problem. So my claim is in that this is a single variable problem. There is only one unknown, finding which you can pretty much find everything in the circuit. Can someone spot that one single unknown? There was one unknown, finding which you can find pretty much anything in the circuit. So to find that one unknown, you have to write one equation. Source transformation, then on. So we already did source transformation. Fine. Source transformation, then no. Even before source transformation, there is only one unknown. So just in case you are confused, it doesn't hurt to ask this one question. Current in branch, fine. So how do you find that current in branch with a 2 ohm resistor? How is that? If you know that, how do you know everything else? Okay. voltage across 3 ohm. General things voltage across 3 ohm. Fair. It helps to ground one of this. Okay, reference voltage. You ground this. If I put the ground here, or if I put the ground here, does it matter? Whether I put it here or there? It's all, it's all zero. Notice. This is all zero. Where I put the ground, that doesn't really matter. This is all of the same voltage. They're connected by wires. Negligible resistance as far as the circuit is concerned, rest of the circuit is concerned. Where you put the ground is immaterial at the bottom. It's all 1 point. For that same reason, if you look at the voltage across 3 ohm, the same voltage here is the same voltage here. So it's all at the same voltage. See again, so Girish, if you are taking that route again, you're like when you're presuming 0.5, you're likely doing source transformation. Okay. So we did it, we solved the problem, but it's just right now nodes. In fact, this is what I was trying to explain here. Hey, this is all, the whole top thing is at the same voltage. The whole bottom thing is at the same voltage. Essentially, it's the same point. Electrically, it's at one, essentially it's a 1 point. Electrically, it's a single point. Electrically, it's same potential. It's a single point. It's a single point. So if that voltage is an unknown, okay, current entering that point is 2 amps. Current exiting that, let's say, yes, a current here, a current here, and a current here. We can all write that, all of that in terms of V. Okay, 2 amps equals the 3 currents. The 3 currents are V by 4 plus V minus 2 by 4 plus V by I1, I2, I1, I2, I. So net current entering that as 2 amps, exiting that node as I1 plus I2 plus I. Can you quickly solve for V here? I think that's fairly easy, right? So what this is, V equals dash volt. The current through that is 1. So V should be, I think, V is IR. V should be 1. Hey, V should be 1 by 3, I suppose. Yeah, not 1 by 8, 1 by 3. V is 1, this is, current is V by 8. I suppose this is 1, okay? That implies your current 3, that is current through R 3 ohm, okay, equals, technically you don't have to do this. Power in the 3 ohm, V square R. I don't think this is 1. If you solve it, I think you should get 3. And just someone confirm that. You should get 3 volts. So if you multiply by 12, you have 24 equals 3V plus 3V minus 6 plus 4V. All of us are getting different answers. 30 by 10 equals 3. So Janelle did 24 minus 6, 18 by 10 is it? I suppose Janelle said 1.8. No. I suppose he did that. Yeah, 3 volt. So 3 volt and then you get this power to be 3 volts. The answer is. Yeah, be careful about it. Of course, you could also do at this stage. This implies IR3 is 1 amp. From that, you can get powers. But also, you have V, I, given 2, you can find the other. I prefer writing this as V, I, or given any 2, you can find the other. Given any 2 in the set, V, I, or you can easily find the other. Fairly easy. And then you have power equals I square R equals V square by R. You also need to know a couple of things. Variable SI unit. This is current. You have amps, resistance. You have voltage. You have volt. Okay. Notice. So you have voltage actually technically equals ampere dimensionally. In fact, SI, if you're calling SI, 1 volt equals 1 amp into ohm. And then you have your power. This is in watts. In fact, 1 watts happens to be equal to, you can either say ampere square ohm, or better is VA. V into voltage into ohm. VI is power. So in this question here, what is the power dissipated in a 3 ohm resistance? Equivalently, they could have asked you what is the current in the 3 ohm resistor, what is the potential in the 3 ohm resistor, right? So based on the same concept, okay, they could have equivalently asked, they as in the gate committee, equivalently, they could have asked IR3, VR3 ohm, simple modification. We tend to forget this. I'm going to do a quick poll. We call that apply. One as recognize where source transformation is potentially useful. Potentially not electrical potentially useful. It's like possibly, probably useful, potentially useful. One thing. Second is apply voltage and current division. Third is, KVL, KCL, at least, KVL, KCL. Do Norton, basic Norton, do basic Norton Thevenin conversion. One is to recognize, one is to apply Thevenin conversion. One more thing that we learned is look for single variable problem in circuits. Let's do a quick poll just to recall what we learned. You consolidate that before moving. Say before this, you may not have known voltage and current division. We half the class order. That was understandable. But I explained you. Two resistances, how does current get split? It's a fraction, right? Again, two resistances in series. How does the voltage get split? Again, it's a fraction. Just look for it. Look for if in the top, is it all one? If it's the same wire, okay. If it's all wires at the top, probably the single variable problem. Wires at the top and wires at the bottom is a short sign of a single variable problem. So, to this mix of sources, mix of potentials and amperes, it is hinting you, probably source transformation. There's one long wire at the top, one long wire at the bottom, okay? The one long, green wire at the top. You likely there's one variable. If I solve for it, I'm done. Great. So, most of you, okay, fair. Source transformation is fine. Voltage current division is fair. Okay, we are kind of struggling, but we go over this once or twice, we'll get it. Not on the fine thing. This is fairly easy. Look for single variable problem. I don't really agree with it. Fine. Okay. So what I'm going to do is, you can solve this in a couple of ways. Solve this as a single variable problem. That's your task. Tell me what is that one variable, knowing which you know pretty much everything in the section. You have to name that one variable here, knowing which you know pretty much everything else. It's like one equation, you can solve this. Right? So your task is to not solve this problem. Your task is to identify that one variable using which you pretty much know everything. Or fine, yeah, I can see, or Thevenin is not the one variable here. Not yet. You can solve it with the Thevenin transformation. That's a different thing. But it's much faster to recognize there is one unknown there. Look for long patches of wire in the top and bottom. In the bottom, make it ground. In the top, make it an unknown. Where is the long patch of wire? So method 1, is there a single unknown? This is a one variable problem, single variable problem. I'm just asking this question right now. Okay, not so long, but notice this is essentially one limb. Three things are in parallel. Okay, this is one of the parallel limbs. This voltage is same as this voltage. This voltage is same as this voltage. You might as well ground it. And notice VA is your only unknown. In terms of current, there is a current in 10 ohm. There is a current in the other loop. I1, I2. There are two currents. Voltage, there is only one voltage. The answer is yes. That one variable to begin with is VA. That is, what I mean is, you can directly solve for that one variable. No 2-3 equations. One equation you can solve for that. Yeah, 24 equals 12 minus 68. Probably you're doing some sort of source transformation. Okay, I will also do that, but notice here current entering is 1.2. Let's kind of draw this 20, 20, 10, 24. 1 point. My claim is there is one unknown voltage here. It is all at the same voltage. It's a wire, right? Piece of wire, same potential, same voltage. Let's ground this. Whether you ground it here or whether you ground it here, it's all one and the same. It's the same point, I think. All three are one and the same. There is a current, let's say I1, if there is a current I2. Notice what is entering is 1.2 equals I1. You don't have to write it I1, but this is essentially VA by 10 plus I2. It happens to be VA minus 24 by 40. To be consistent, this is VA by 10. What I have here is, I have I1 here, I have I2. VA is the only unknown. You can solve one equation, one unknown, you can solve for it. See, other times, typically you will have two equations or not. This can equally solve for it. This is 20 and 30, right? So, this is 30, so this happens to be 50. Hey, can someone now solve for VA? What is the value of VA? So, your VA happens to be multiplied by 50. 1.2 into 50 is 60. And you have 5 VA. There you have VA minus 24. And we have to be careful. Notice this is given to be this direction I30. That is what at the end of the day we want. Oh, that's not what we want. Fine. 60 minus 24, 36. 5, 6 by 6. 5 volts or 6 volts? One of that. Can someone just confirm that? So 60 plus 24 equals 6, 14. 84 by 6. I'm going to go ahead and write this, okay? If I multiply this by 60, I get 60 equals 5 VE plus VA minus 24. The VA happens to be. Okay, so where is this 5 volts coming from? I'm puzzled by that. Even I am getting VA happens to be 84 by 6. Happens, I suppose, is 14. Okay, this is 14 volts. That implies current will be, or what do we need? The voltage across the terminal, right? This is at 14, this is at 24. There is a drop. VA minus VB is at 24. This means we can actually answer this. From 14, it goes to 24, right? So notice VB equals 24. VA minus VB, that would be minus 10. And this truth I can answer. Yeah, I can answer. Minus 10. Where was this 5 volts coming from? Just wondering, like, that one equation, I did solve it in mind. I got like 12 by, I thought 72 by 6. I thought 12. Okay, then it's not 70. Actually 84 by 12. Fine. 14 I understood, but why was this 5 volt? Where was this coming from? Again, you did 60 minus 24 by 6. Even that should give you 6 volts, right? 1.2 into 50 is 6. Okay, fine. This big easy. In fact, I really don't do this in the mind. Okay, we have a get calculator, right? During class, I use a calculator. So use it. Right now, I don't have a calculator, which is why I am kind of, at least, while waiting for the answer, I'm doing that in the mind. But use a calculator, okay? Avoid it. But fine. In fact, what I'm noticing is this is one equation. We have trouble solving that one equation. Fine. We'll keep that as a last resort. Let's also go back to our first resort. This is typically that, silly mistake proof. Here also, of course, silly mistakes are possible, but, this is typically better. Method, did they call it method 1 or method 2, right? This is method. There isn't a mix of, again, mix of sources. There is a mix of sources. Do source transformation and do it conveniently. That is hinting that consider source. Am I audible now? Yeah, so there is a power cut, but we'll continue. Okay, the system that I have works with. Okay, so there is a mix of sources that was hinting that consider source transformation. So, hey, if I transform this, I'm going to get one single loop. Okay, so notice if I transform that, so I have the rest of the circuit, 20, 30. This, that part of the circuit, I'm going to do a Thevenin. Why there is just one loop, you can, now you can just write it down. The one equation is the answer. See, only difference here is, here you wrote one equation directly, you didn't do any transformation. Here, after the transformation, one equation you can quickly get. Okay, so what we have, let's fill out the easy ones first. 20, 30, I'm not writing the units because fairly obvious. 24. So this 10 remains a 10 and this is just 12 volts. Fairly easy. Okay. From here, it's just, one equation, one. You can find the current here. You can find current, right? What you have here is 12 minus 24 by 60 equals I. This implies your I suppose, is 12 by 60. How much is it? Minus 12 by 60. So this is a negative number, minus 2 by 60, suppose. 2 by 10. 1 by 5. Okay, minus 1 by 5. Minus 1 by 5 amps. Okay, and then from there on, you have the AB equals I times 50. That equals minus 1 by 5 into 50. So your answer is minus 10. Again, be careful about the sign. This is minus 10. Current flow doesn't flow this way, but it is flowing the other way around. And while writing this equation, notice you're writing KVL, Kirchhoff voltage law. Okay, while writing this equation, sum of currents is 1.2. We wrote Kirchhoff current law. Okay, although we didn't explicitly see that, right? We are kind of starting to apply that. Okay, fairly easy. Let's move on. Power consumed by the 3 ohm resistor. is 12 watts in the given circuit. Value of the resistor R in the circuit. Okay, strategies for this. Strategies. If you want me to enlarge this, what is there in the 3 ohm circuit is 12. What we want to find is this R. Hey, while I am waiting for a response, notice some trivial things, okay? Many things, it's very hard to improve performance, okay? Acutely, suddenly you just do this, magically improve your performance. There are not many things, but to spoil your performance, there are many simple things, many easy things you could do that can easily spoil your performance, right? Dehydration is one thing, because I'm here. Dehydration is one thing. Typically, Saturday classes, I used to fast, because intermittent fasting, typically Saturdays, 1 day a week, it's good for the body. Based on physiology, I used to fast. But so it's actually very hard for me to take Saturdays classes. So I have decided not to do that on a Saturday, but do it on some other day. So there may not be a superfood to improve your performance on the examination day. But if you skip the meal, okay, your sugar levels are going to go down, hypoglycemia, your brain is not going to work the way you want it. Basic, a decent meal, average size meal, again, too much, it's going to, your digestive system is going to imbalance, put your brain in imbalance. And then, too little, again, your brain will be in imbalance. So average amount of food is essential. If not, you can easily spoil your performance. Proper dehydration, that is a must, okay? Normal ones, just carry a water bottle, I suppose that is allowed. Or even otherwise, there should be drinking water available. Feel free to go every half an hour or something like that. Feel free to have a cup of water. And so during classes, don't get to this habit of, during your classes, don't get to this habit of having a snack. Because notice, you are controlling your glucose levels in the blood. Okay. By that, you are also controlling the fuel that is available to the brain. You may not be able to do that during the examination. You may not be allowed to snack during the examination. So how you perform, 3 hours I can easily manage. I can do mental exercise. That's what you might be thinking. But on the examination day, because you are not allowed to snack, it can actually hamper your performance. And ideally, most examination halls are air conditioned. So if you are not used to, this cold room, okay, don't drink lots of water, else you are like running to the restroom every 30 minutes. Drinking water is like 2 minutes. Restroom, it takes like 10-15 minutes, right? So be aware of this. Very hard to acutely, that is on the examination day, you cannot do something to drastically boost your performance. But on the examination day, you can do something silly to actually drastically decrease your performance. Be careful about it. Food, hydration, ventilation, or, the environment, your posture, okay? Don't take that for granted. Whatever you do in the examination hall, try to start recreating that. Okay. With that, the current here is on. Yes. So I suppose the strategy is, from that we get the current. We get the current in the 3 ohm. Yeah. See, if you get the current in the 3 ohm, you don't know the current, right? You know the 3 ohm current. What can you do with it? You see, this is an unknown. It's not a single variable problem. It's not a mix of sources. But this is like right? It's not a mix of sources. Mix of sources. Let me get the scale correct. I'll zoom in one in. Is it a mix of sources to consider source transformation? No. Is it a one variable problem? No. Are there stretches of, I try to draw this here. By the time I draw, there is a jump here, and we kind of know, right? Even if you were to ground it here, notice, okay, this is a 10. This is one variable, but again, you run into this issue of what is this current here, right? You cannot solve for this voltage because you don't know this resistance. You cannot really solve for. Again, that trick doesn't work. And this is what I called. Can someone complete that? I want to write a word, but I have written like partially. Can anyone complete that? Hey, this meeting is still on, right? Let us confirm that. Yes. Can someone complete the word now? Seriously? Yeah, this is what I'm going to refer to as the Sudoko network. Sudoko problem. It's like you start filling in details. Wherever it's possible to fill, you kind of fill and quickly realize, hey, all details is fillable. It's actually a very rare problem, but the moment you identify it, you can easily solve it. Okay, so I gave it a special name. This is 12 volts. So I know the current. Current is I square R is 12. So I suppose that is 2. I is 2. Agree? That is my step 1. My step 2, I know the voltage across. I'm not short circuiting it. I'm trying to find the voltage across that. I know that. This is voltage there is just IR 6 volts. Let's zoom this a bit at this stage. I know this voltage 6 volts. This is step 2. So this is at a higher potential. Current flows this way. It's not like, current flow direction is the same. It's not like R is 13 ohm. Yeah, we'll come to that. Okay. So at this stage, I know the voltage drop, but I do not know the current. At this stage, I cannot answer R. I need more information. I need somehow the current. I need to look at the rest of the circuit for that. I need to know the currents here. Right? But quickly, hey, I just solved this. This is 6 volts. Step 2. This is 10. This is 6 volt drop. That means this drop is 4 volts. That is step 3. There is a 10 rise. There is a 6 drop. It has to be drops, okay? It cannot be, current cannot be in different directions in this resistor. They are all parallel. Only the values can, magnitudes change. Direction remains the same. Higher potential in the left hand side, lower at right hand side. Goes from, current flows from this side to this side. Current goes from this side to this side. There is no question about it. Okay, so there is a 4 volt drop there. Hey, I know this resistance, so I can quickly find out the current. I know this. I know the voltage drop, so I know the current. This current is 4 amps. This current is 2. This is 2 amps. That is my step 4. Hey, I'm essentially, I'm doing what we will do in a Sudoko. 4 amp, 2 amp. Is that correct? Potential of 4, and then there is a 4. Okay. I know 4 amp, 4 amp. So this is 6 amps. Call that step 1. 6 amps. That is step 5. And I know this resistance. So this potential I know is like 6 volts. I kind of know this current. I can fairly write it at step 1 itself. And I'm going to do that here. This current. How much is that current? That is 3 amps. How do I know that? 3 times 2 is 6. The drop that I know. So total current is 6. 2 goes here. 3 goes here. 1 goes here. That is the last step, and I think you can kind of get the answer there. So again, to be careful about the units, this is 2 amps. That is of course, my first step. That is in blue. My last step, the current. Steps 1, 2, 3, 4, 5. Then we'll do 6. IR equals 1 amp. What is the resistance? See, each step, there is no equation, no solving and all. I just use V is IR everywhere. But I kind of traversed it, essentially what we do in a Sudoko, I did. Why I did that? Hey, gate problems has to be solved in 2, 3, 4 minutes. Except there are 1 or 2 questions deliberately implanted to waste your time. Okay, to make the uninitiated waste time, crucial time during examination. The committee inserts 1 or 2 time wasting questions here and there. You stood for 2 days, we cannot solve it. They deliberately inserted. So is the student smart to avoid it? That's what they want to check. They don't want to check if the student smart to solve it. They want to check if the student smart to avoid it. There are always 1 or 2 questions. So typically, if you are 1 page derivation, if it's going beyond that, I would skip that question. Any question. That 1 or 2 marks is not worth that. So here, notice I haven't done 1 or 2 page derivation. My known tricks, a simple resistance circuit. Is it a mix of sources? A single variable problem, no. Then special case, say Sudoko, can I do this solve it just like that? Yes, this happens to be 6. Okay, so this is 330. 4 will likely give 430. Okay, yesterday itself we finished kind of early. Okay, so let's summarize. We have done KVL, KCL, equivalent, series, parallel, and delta Y also. Let's say okay, it is there in the recorded videos, there in the notes. So in some assignment problems, this is a KVL, KCL. Then what else? All basic power calculations. V, I, R kind of problem. And then P is I square. These are the kind of problems that, and here we used. So far, specifically again you have to list the sources. Then single variable. Single variable is typically single voltage. Okay, single variable. We have also seen miscellaneous Sudoko, miscellaneous. And they can do few more things with the Wheatstone branch. Yes, this is all 1 semester's worth of electrical circuits, okay? We are doing that in a couple of hours, maximum couple of weeks. Okay, so lot of condensation, evaporation, all of that is happening. Information is getting condensed as well as it is getting evaporated. There is this memory retention problem. So they can ask you a few more things with resistance, but fortunately they are also fairly easy. One is called the max. There is a power theorem. There is this. What should be the resistance value so that the power dissipated in it is maximum? Then there is a Wheatstone bridge. In fact, I should put it this way. Typically, they ask you this. One question from here, one question from here. You get two questions from what we are learning today. If you are fortunate, Wheatstone bridge, sometimes 3 questions, but yeah, you need some AC bridge concepts. So yeah, typically, you get 2 questions from what we do today. Okay, so now let's look at max. In the circuit given below, what should be the value of resistance R for maximum dissipation of power in R? Concisely, can you tell me, how do you find R? Concisely, as concise as possible. Sir, that resistance should be equal to this. You can state it equal to this. You can state it in 2-3 words. I don't want to say you do this series parallel conversion, pi delta conversion. There is a pi network, sir. You can do that. You can do the y, or there is a delta. You can convert y. None of that I'm asking. Single variable source conversion. None of that. R has to be this. 2 or 3 words. R equals dash. Not a number. Couple of words can fill that. In other words, when they say what should be the value of resistance R for maximum power dissipation in R, that is, they're asking a slightly different question, equivalent question. In the circuit given below, this whole sentence you can replace it with one word. You treat this as a load, Vs RL. No, RL, yeah, that is RL. No, R load doesn't really help. You have to look at the circuit. You have to get something from the circuit. In fact, so you can answer in 3 letters. So, Janil, which question are you referring to? Is it's time consuming, but we can do just trial and error. No. This again is an easy question. If you know what they are asking, it's a very easy question. It's not time consuming. Chanakyan is fairly close. He said 2 letters, RL. I think the answer is 3 letters. R is one of them. There are 2 more letters you have to fit in. For max power dissipation. Or transfer theorem, 3 words. I should give credit, okay? If not 3 letters, I should give credit for this. For the questions or the conditions stated, R equals 3 letters or given is power transfer theorem. Power transfer from this part of the circuit. Notice it's a linear circuit. You can essentially put a Thevenin equivalent there. From that to the load is maximum when the circuit's Thevenin resistance is same as the load. This is a circuit. The load here. And write this as load. You can see this as a load. Now, if we quickly notice this part of the circuit, let's keep RL that way in the 2 terminals. Let's draw this. This entire circuit can be replaced with 1 voltage source, 1 resistance. This happens to be V Thevenin. This happens to be R Thevenin. For maximum power dissipation in the load, RL has to be equal to R Thevenin. That is power transfer. This goes by the name power transfer theorem. So what are they asking? What are they asking? They are asking you to find R Thevenin, right? So the whole question in other terms can be stated as find R Thevenin, which is what they have stated this way. What should be the value of resistance R for maximum maximum dissipation of power in R? In simple terms, find R Thevenin on this. Okay, is this question clear? We'll go, sir, how do you find R Thevenin? I haven't really explained that, so we'll have to. Hey, there was a minor connection issue. Hey, can someone tell me what is the last thing you heard? There was a minor connection issue. I just tried to change the connection. Power is back on. You put it in that fiber. Hello. Am I audible? Hello. Okay. I didn't get response for the power transfer theorem. So I said the question essentially says find R Thevenin. That comes from power transfer theorem. Are you all with me on that? Because the theorem says for maximum dissipation, load resistance equals circuit's Thevenin resistance. So now the problem is, the question is essentially find R Thevenin. That is what power transfer theorem says. That Kirtana answered that. Now the question is, sir, how do you find R Thevenin? We know how to go back and forth from Thevenin to Norton. But from circuit to Thevenin, how do you do that? This is what I was about to do. Norton to Thevenin, right? This stuff we did. But how do you go from any circuit to Thevenin? Once you go to Thevenin, you can go to Norton. But how do you go to Thevenin? That's what we are going to do now. Circuit to Thevenin equivalent. So to find R Thevenin, remove all sources. In fact, remove all sources. Let me be more explicit. Remove, that is, you are either going to short or open. Short or open all sources. That is, sources as in voltage. If it's a voltage source, you're going to short it. If it's a current source, you're going to open it. Okay. To remove all sources and find our equivalents. That's it. Remove all sources. How do you do that? Voltages you have to short, current you have to open. What do we mean by that? Let's look at an example. Let me redraw the circuit. So how many sources do we have here? I have one source, one voltage source. How do we remove that? Should I open or short circuit that? I should short it. This is shorter. Essentially, I can remove that voltage. This is short. By that, I can remove this. What is left is only resistances. I can find R equivalent for that. R Thevenin equals R equivalent here after removing all sources. Can someone quickly tell me what is the equivalent resistance here? Fair, no? This is 2 and 3 in parallel, that in series with 1, 2, 3, 1, all okay. Okay, what else here? R Thevenin equals R equivalent here. That corresponds to 2 parallel to 3 plus 1 kilo. 2 and 3 in parallel, that is 6 by 5, 1.2. That equals 2 point. That is your notice. So Thevenin is for the rest of the circuit. So I didn't put that RL here. Don't put RL and find, sir, there is RL in parallel with 2 and 3. This 1 in series with 2 and 3. And there is also RL. Don't put that RL there. It's like across the terminal, one is the rest of the circuit. That is what we are looking at. Be careful about. Let's also find VThevenin. Sometimes we are required to do. To find VThevenin is essentially voltage across RL, across a load, voltage across a load resistance. And we slightly improve this across voltage across open terminal R. Voltage across open terminal. You are removing RL and then what is the voltage there? You are not finding voltage with RL. So you are removing RL open terminal R. Because again, this is for the rest of the circuit. This is not pertaining to load. You can put any load, right? Let's also go ahead and do that. Moreover, I have solved the problem. Moreover, to find VThevenin, not required for problem, let me take not required for given problem, not required for given problem, just in case they ask a given problem. Again, remember, you have a load. Hey, when is this Diwali, by the way? I'm starting to hear some crackers being burst. You can put a little more. I suppose my neighbors are bursting crackers. So rain, storm, Diwali, we will conduct this class. Rain or shine, we will conduct it. Yeah, I remove the load, open terminal. What is this voltage? 21st October. Okay. So notice the moment I remove that load, this is essentially 1 point because no current goes there. It's open terminal. If I were to ground this, okay. If this is V in or this is, let's say, VR. Okay. In fact, this happens to be VThevenin because current here is 0. This is open terminal by definition. To find VThevenin, you have to open terminal across load. So we have opened it. Current there is nothing. It's not connected. Current cannot flow. For that reason, this is also VThevenin. These two are one and the same. And this VThevenin is fairly easy to find. You have 10, you have 2, you have 3. Can someone tell me what is VThevenin? Hey, time is 4. We'll finish at 4:30. Okay, some 15 more minutes. I have to do which stone branch. Oh, perhaps let's finish with this problem. I told you which stone is a different. Let's just look at an example of finding VThevenin. We'll wind up. How do you find VThevenin at this stage? Fairly easy. I hope someone answers this. Notice the voltage across this terminal. If I ground it, these two are the same, right? These two are the same. No current flows in that resistance. So what is the voltage here? That's what we want. You can write it down. VThevenin is a voltage here. If you do not follow, at least you should raise an issue. Or is finding VTH somehow difficult in the circuit? I also said see that problem is solved. One RL has supposed to for maximum power transfer, power dissipation, RL has to be RThevenin. Found RThevenin, we solve that problem. I'm just telling you how to find VThevenin. For instance, how to find VThevenin, I'm showing you an example. Nothing more. I'm not solving this problem anymore. Let's in fact erase this. You're like, sir, what will be? It's all what is happening here, right? Let's erase this. Let's erase all of this. Just how do you find VThevenin? I'm giving you an example. Or do you have doubt, sir? Why is the red VThevenin same as the gray VThevenin? Is that your question? I said VThevenin is this voltage. Okay, let's say this point is grounded. It's all the same point at the bottom. It's all the same. It's all the same, right? And I said, this is VThevenin. Why? This is VThevenin. Why is this? Where are you stuck? Where are you stuck? Let's Pritijat. Purna. Okay, Pritijat is kind of answering it. Fine. So I suppose none of you are stuck. Guru, Karthik. The current here is 0. 10 gets, total voltage here is 10. Across 3 is just a fraction of 10. What fraction? You know that. Voltage division. And why do we put a equal to there? Not else. V7 equals a fraction of 10. What fraction? 3 by 2 plus. Okay, fine. Let's do a quick poll and then we'll wind up, okay? So 2 months in the semester is over. KVL, KCL, basic equivalent circuits, Norton Thevenin conversion. Between Norton and Thevenin, you can convert. From a circuit also, you can convert. Power calculations you can do voltage current application. What you have done is Wheatstone bridge. Last bit that we did here is, how do you find RThevenin? Remove one sources. If it's a voltage, short it. If it's a current source, open it. Then find equivalent resistance across the load. Find VThevenin, voltage across open terminal or that's it. Okay. So I think most of you kind of will come back with Wheatstone notice. What we'll do in the next class? Wheatstone, there is a question every year. And then first order circuits. We'll move on to first order circuits. Again, first order circuits. What does a capacitor do? What does an inductor do? That's fairly easy. RC circuit, a lower R circuit, energy conservation, impedance, transient response. So you can say this is fairly easy, okay? The question so far has been, most questions has been very, very easy. So we'll do that and then there is second order circuit.